Assalamu alaikum wa rahmatullahi wa barakatuh, everyone. This is Team G2. Today we'll be giving you basics of vibration, which is lesson 2 for week 2. The subject is fault diagnosis, Minj 472. Our instructor is Dr. Saeed Asiri. I'll start by team management. Our names: Muhammad Bukhari will be the motivator, Ahmed Harbi will be organizer, Muhammad Khudri is our team leader, Khalid Abdin is our recorder, and Abdullah Warsam is our timekeeper. So, our table of content, what are we talking about today? We'll be talking about vibration terminology. We'll start with that, and then we'll go a bit on equation of motion, critical damped, over damped, stuff like that. And then forced vibration, we'll end with forced vibration. I hope you enjoy it, and yeah.
Hi, I'm Abdullah Warsama, and I'll continue with you starting from this slide. At the very beginning, there are some important terminologies used in fault diagnosis that you should know. One of them is peak value, which is the magnitude or the maximum value of a given signal. For example, look at this signal. It begins from 0 up to a certain value, which is the peak value. Another terminology is the mean, or sometimes called average value, which indicates the steady value. It's given by this equation that x bar equals to limit when t goes to infinity 1 over t integral from 0 up to t x of t dt. And also it can be defined in another form of summation form. It says it's 1 over n sigma I starting from 1 up to n x of I. Now comes another important terminology, which is the mean square value, which plays an important role to find the RMS, as we'll see later on. The mean square value usually associated with the energy of the vibration, and it's given by this equation. It's basically the same equation of the mean value, except that the x here is raised to the power 2. Now let's take an example on mean square value. It says, given that x of t equal a sine omega t, determine the mean square value. Mean square value, by its definition, is given by this equation. And t is the period of the vibration, and it's given by 2 pi over omega. Now, as you see, there is an integral of sine square, which is difficult to integrate a sine square. So we're going to replace it with another expression, equivalent expression from the terminology, which is this one. And then substitute in the main equation. There we have, this is going to be like here. As you see here, it's going to be limit when t goes to infinity a square over t, and this is the sine square omega t dt. And don't forget the interval of integration. It's starting from 0 up to t, which is 2 pi over omega. Then it gives you the final value, which is a square over 2. The other terminology is root of mean square value, which is simply the root of the mean square value. So take this final answer and take the square root of it. This root is going to go with the square here, and this 2 is going to be square root of 2, as you see here. Decibel, or dB, it's basically used to measure the sound level, as you can obviously see here in this picture. How loud is too loud? For example, when you hear let's take hair dryer or fireworks, whatever. As soon as you go up to 90, say 90 or 85 dB, there is some loudness that's not recommended. For example, it will cause hearing damages and headache and so on. But it's also used widely in signals and vibration systems. dB is basically the ratio of a magnitude to another reference magnitude. It says Lm is 20 log 10 x1 over x2 dB, where x is the magnitude. For example, if the magnitude was the power of certain system, then it comes like LB equal 10 log 10 B1 over a reference B dB, which where B is the power. Let's take some examples now. It says that velocity of vibration is measured as 2.5 micrometer per second. What is the velocity level with respect to the reference velocity of 10 to the power minus 8 meter per second? Velocity level is basically the decibel. So it's gonna be like that. LV, which indicates the velocity, equals 20 log the velocity given here, 2.5 micrometers per second, over the reference velocity, which is 10 to the power minus 8, it equals to 48 dB. Okay, example 2. A harmonic motion has an amplitude of 0.2 centimeter and a period of 0.15 seconds. Determine the maximum velocity and the maximum acceleration. The harmonic function is given by this equation, and A and T is given in the equation. So omega, by its definition, is 2 pi over T, which is 42 radian per second. So from this function, we can differentiate once and 2 times to get x dot and x double dot. So this differentiation will lead us to these two equations, as you can notice here. So what is the maximum? We were asked here to determine the maximum velocity, which is the omega a in case of the velocity, and omega square a for the acceleration. Okay, example 3. It says that an accelerometer indicates that a structure is vibrating harmonically at 82 cycles per second with a maximum acceleration of 50 g. Determine the amplitude of vibration, given that the gravitational acceleration is 9.8 meter per second squared. So from the previous differentiation that we just made in the last step of example 2, we can conclude that x max is equal to x double dot max over omega. Then we need to calculate omega. Omega is given by 2 pi f, which is 515 radian per second. Okay, then just plug the value of omega and the value of x double dot max, which is given here, and you will reach to this value. Okay, the last example we have here is, it says that a harmonic motion has a frequency of 10 cycles per second and its maximum velocity is 5 meters per second. Determine its amplitude and its period, also its maximum acceleration. Let's at the beginning find omega. Omega is 2 by f, which is f is given, which is 10. So omega is 62.83 radian per second. T by definition is 1. It's the reciprocal of the frequency. So T is 1 over f, which is 0.1 second. X dot max is omega times a. Then we have x max and we have omega, then we need to find a. So a is gonna be x dot max over omega. X max is omega squared by, times a, as we defined previously in the example 2. Then you just plug the values of omega that we found here in the very beginning, and the value of a, which is 79. Then x double dot max, which is the maximum acceleration, is 311.86 meter per second square.
Assalamu alaikum wa rahmatullahi wa barakatuh, everyone. This is Muhammad again. I'll be commencing the PowerPoint, I'll be commencing the presentation. So, I'll be talking about the equation of motion over single degree of freedom, free vibration. So, when I say free vibration, I mean there's no external forces nor damper forces. So, we've got two types of equation of motion, two types of procedures we can follow to get the equation of motion. First procedure is Newton's method. That's not a procedure, it's a method. So you've got Newton's method and you've got Lagrange's method. Whatever catches your flow, use it. Whatever is more easier for you, use it. I'm going to give you the pros and cons for each method. So Newton's method is good for simple system. So I've got little components, not much of components, not very complex system. Newton's method is much preferable. It'll save you some time. Lagrange's method is good for complicated system. So if you've got like a pendulum, you've got some springs, a lot of masses, it's cool to use Lagrange's method. It's quite easy. Newton's method is vector based, so you've got a sense of direction in the situation. Yet Lagrange's method is more scalar based, so you have equations that you use. It's more energy based. By energy based, there's you took in Minch 470. We have two kind of energies. We've got potential energy and we've got kinetic energy. Newton's method needs all constraints to be defined, but Lagrange's method does not need all constraints to be defined. Newton's method has no general procedure. So basically you just draw the free body diagram, do your force analysis, and hey, you get the equation of motion. Yet Lagrange's method, no, you have to identify how many degrees of freedom. After that, you need to bring the kinetic energies, the potential energies, get L, which is equal to T minus V, and after that do differentiation and you'll get the equation of motion. So what I'm saying here is do whatever is more simple for you. In this example, we'll use Newton's method because this example is quite simple. It's a simple system. So Newton's method would be much more preferable. So I'll go to the next slide now. So let's start. Equation of motion for free vibration for a single degree of freedom. Why is it a single degree of freedom? Check the mass over here. It's only going in one direction. That's why it's a single degree of freedom. Upon making, remember I told you we have Newton's method and Lagrange's method in the previous slide. So here we're going to use Newton's method. As you can see from the force analysis, we've got mg, normal force, going up. This will sorry, I'm just going to put the pointer over here. So mg is going to cancel in, and you're going to have a spring force. Okay, the movement of the particle is going to the right. So we know that sigma fx equals to max. Upon force analysis, we know that the forces it's affecting is the spring force, so it's going to be negative kx. As the body is moving to the right, there's going to be a reaction from the force that's pulling it to the left. That's why it's negative kx. And we know that ax is the second differentiation of displacement. So negative kx would be equals to md square x by dt squared. You can also write in this way, it doesn't matter. There's a couple of important notes from the previous slide. Just notice that mg cancelled in, put that in consideration, and that we used Newton's method to acquire the equation of motion, not Lagrange, Newton's method. Now we want to solve the equation of motion. So what do you notice different from the previous slide? This is what we notice. We transferred k over m to the other side, so we got it over here. It was here. We transferred it here. And then after that, we divided by m, because at the end of the day, we want to bring the natural frequency. So it's saying it's a homogeneous second order. Why is it second order? Because the differentiation is second order over here. Why is it linear? It's linear because we don't have signs. It's not x dot, x double dot. That's why. It's an ordinary differential equation, d by dt. If we had partial here, we'd have had another story. And constant coefficients is equal to 0. That's why it's constant coefficient. We're going to assume a solution. Our trial solution will be xt equals to c e raised to lambda t. When we plug it in, we'll get, okay, how did we get this equation? I'll tell you how. You see this x of t, you need to differentiate it twice. When you differentiate it twice, you'll get that x of t will be equal to c lambda squared e raised to power lambda t plus k over m, and what is x? X is equal to c e raised to lambda t, which is equal to 0. When you take a common value, you'll get that this quantity plus k over m, all in parentheses, is multiplied by c raised to the e raised to lambda t. You notice that c multiplied by e raised to lambda t is impossible for it to be 0, because if it's 0, there won't be vibration. So the only conclusion we can come to is that lambda squared plus k over m will be equal to 0. So that's where we get the characteristic equation. Our solution for lambda will be equal to, we want the natural frequency. So we're going to transfer this in the other on the other side, and then we're going to take the square root. The square root is going to be negative positive of square root of negative k over m. This negative is going to be a complex, so it's going to be I, and we're going to put it outside of the root. We'll get the final solution will be positive minus I raised to multiplied by square root of k over m. That will be equal to positive minus I omega n. Omega n is equal to the square root of k over m, which is the natural frequency. The solutions for xt are the child solutions that we used. It's going to be equal to, when you substitute this quantity over here, you'll get that the solution of xt would be equal to c1 e raised to the power I omega t, and xt equals to c2 e raised to the power negative I omega n t. So solution for xt is then a linear combination of the two possibilities. So the solution for the final quantity x of t is going to be the summation of the first solution and the solution, because we have a positive quantity and a negative quantity. So it's going to be the summation of both. Important notes from the previous slide: we divided by m in order to get the natural frequency, and we assume the solution xt equals to c e raised to the power lambda t. So we got so as you can see over here, we have two unknowns. Two unknowns include c1 and c2 from our solution. The two constants c1 and c2 are fully determined. So in order to get c1 and c2, we need to know initial conditions: xt equal to 0 and x dot at t equal to 0, which is the velocity quantity. By using Euler's equation, we can plug this equation in here to get the xt equals to a cosine omega t plus b sine omega t. Differentiate this twice. Okay, when you differentiate this equation twice, when you differentiate this equation twice and you plug in the initial conditions, you'll get that the constant a is going to be equal to x naught, and the b will be equal to v naught by omega n. When you plug these two in the initial in here, you'll get the following equation. You'll get that xt is equal to x naught cosine omega t plus v dot by omega n sine omega t. So that's going to be your solution. Which can also be written as xt equals to x, which is amplitude, and this is the phase change, x sine omega t plus the phase change. So x is equal to this quantity, and the phase change is equal to this quantity. Very important notes to remind yourself from the previous slide: you have to differentiate x twice. Xt equals to a cosine omega n t plus b sine omega n t twice in order to get the velocity term to substitute in the original equation of motion. As you can see over here, this is a harmonic graph. So the most important thing is to see over here, x is the amplitude and this is the phase angle. Important things to know that x dot does not start from 0. It actually starts after 0 in a bit. And the slope of this will give you v0. Of course, we know that the natural frequencies units are radians per second, and the frequency is going to be in hertz. And tau is going to be equal to 2 pi over omega n, which is basically the inverse of the frequency. A very important thing, this equation is always used for no damping, no force equations. So if you have a system, there's no damping and no external force on it, you're going to use this equation over here, xt equals to x sine omega nt plus psi. But please bear in mind, in reality, we'll never have a term where there is no damping of force. There will always be wind force, there will always be a damping supplement. This is just for mathematical reasons we assumed it. So in reality, we'll never ever have a term where there's no damping or no external force.
Assalamu alaikum everyone, this is Khalid Abdul Khair with you, and I'm over here to talk about the damped vibration. As we know that every vibrating system has damping. This damping might be due to air resistance, fluid resistance, or the natural damping of the material itself. Now the air resistance and the fluid resistance, we can call it as friction also. Now in this presentation we'll consider only the viscous damping that is produced by linear viscous dampers. Now what this linear viscous dampers are also called as the dashpots, as I have shown in the picture below. You can see that this one's at the low part is filled with, this one is filled with fluid. Now this one is filled with fluid and you can push this up or down. The force and the resistance act opposite way. Or you can also call it the velocity and the resistance, they act in the opposite way. Therefore, if you are pulling it upward, that the velocity is upwards, the resistance would be downwards. But if you're going to push it downwards, if the velocity is downwards, the resistance would be upwards. These are basically the dashpots. Now for the viscous liquids, they have a coefficient called as the viscous damping coefficient, which is called as C. The force that we will apply, or that is the resisting force that occurs, depends on the velocity at which we are pulling or pushing the damper itself. If we pull with a high velocity, or if you push with a high velocity, there will be larger resisting force due to the fluid that is present in the dashpot itself. Also, if you do it slowly, there will be less and lower resistance force. Now let me explain why does this happen. When we are going to pull it upwards, for example, or let's consider we're pushing it downwards. Alright, the dashpot and the cylinder, if we're pushing it downwards, what happens is that the fluid needs time to come up. So if you're pushing it really hard, it does not get the time, therefore the resistance occurs. But if you do it slowly, the fluid can move out easily through the corners, and there will be lower resistance force. And as we have said before, that the force is always opposite to the direction of the motion, and the mechanical energy that we're applying is lost or dissipated to the viscous liquid itself. Now if we would want to have a clear definition of what a dashpot is, the definition is on top. You see, a dashpot is a mechanical device, a damper which resists motion via viscous friction. The resulting force is proportional to the velocity, but it acts in the opposite direction, slowing the motion of absorbing energy. This is what I have explained in the previous slide, that when you are pulling or pushing it, the force will act opposite to it due to the liquids. Now the C, that is the damping coefficient, depends on the fluid viscosity which we have learned in fluid mechanics, and also the plunger dimension, that is the dimension of the plunger, which is this one. Now if we consider this plunger to have a area of 1 centimeter square, we have the viscous coefficient or viscous damping coefficient of air, if we consider it as the standard, is 2.6 10 raised to the power of 8 Newton seconds per meter. And if we want to find the viscous damping coefficient of water, it is 10 times that of air, and it continuous. All of them are related. For example, for oil is 10 raised to the power of 3 multiplied by the C of water. For the maple syrup is 10 multiplied by the C of oil. So this is how the list goes on, and this we can apply depending on what we use in our dashboard. Now let's come to a example of a damped vibration. This over here is a normal or a typical damping system, and this X is the displacement. This X we can consider it as the displacement from the equilibrium. Now, using the Lagrange method that we have studied in vibration, we can get this equation of motion. And then what we can do with this is that we bring this part and this part on the other side of the equal to sign. Then what we get is this equation. After that, we can, as we know that the omega n, which is the natural frequency, is equals to root of k over m. But first of all, we will divide, once we bring all this on the other side, we will divide it all by m. Therefore, as we see, we have m over here, but it will get deleted because we have divided by m, and c will get a m underneath it like over here, and this k will also get a m underneath it like this. And as we have said, as I have said earlier, that omega n is root of k by m, and the zeta is equal to c over 2m by omega n. C is the damping coefficient, and m is the mass, and omega n is the natural frequency. Now first of all, we bring the previous equation from the previous slide and we apply it over here. First of all, we assume an equation of assuming a solution as this one. Then we differentiate it once, and then we differentiate twice. Then we get the first differential, the second differential. After that, we use those differentials and we apply it over here. For example, in this one, we apply the second differential of this solution. Then over here, because this is the first differential, we apply the first differential of this one again. After that, this one does not have any differentiation, therefore we can apply c is equals to omega lambda e raised to lambda t. After that, using our knowledge of mathematics, we can solve it, and we finally come to this equation. And if you look at this equation, we see that it is a quadratic equation where our a is lambda square, b is our a is 1, b is 2 zeta omega n, and c is omega square n, and we can apply it to find the solution using b square minus b plus minus square root of b square minus 4ac divided by 2a. And after we have applied it over here, we get this equation, which is this, and we can use it later on to find out the other solution. So this thing, we can call it as the characteristic equation. Now, bringing from the previous slides, we have come over here and we have brought this equation. So e raised to lambda square, so this is the one value of lambda, this is the other value of lambda, and we can take, as you can see, that e and omega n t are all common in all of them. We can take this common factor out like this, and we can put all this between the in between the brackets, and then this is what we get. And as we know that zeta square minus 1 can be either positive or negative or 0, for an overdamped solution, zeta should be greater than 1, as we have studied in vibration. Then after solving it, we know that zeta square minus 1, square root of zeta square minus 1 always has a real solution, and these are the two possible solutions of being overdamped. And from here we can apply it and substitute in the solution, and this is the result that we get. Also, I'd like to add with this that as the overdamping, the damping is really strong and there is no oscillation occurring in this. Thank you very much. This is the end of my presentation, and Ahmed Al Harbi will continue from here. Assalamu alaikum.
Assalamu alaikum. My name is Ahmed Harbi. I'm gonna to talk about the critical damping response. The system gonna be critically damped when the damping ratio equals 1. That occurs when the critical damping when the damping coefficient equals the critical damping coefficient equals to the square root of Km. As you can see, the critical damped response goes to the steady state very fast. Any critically damped system response is gonna to be as shown in the equation below. The system becomes underdamped when the damping ratio zeta is less than 1, and that occurs when the damping coefficient C is less than the critical damping coefficient. As we can see, the response of the system is going to the steady state while the time goes on, and we can predict the response of the system using the following equation using the initial conditions. When zeta is more than 1, the system becomes overdamped. That when the damping coefficient zeta C is more than the critical damping coefficient. The overdamped response is similar to the critically damped response. It differs in that it takes more time to become to reach the steady state, and we can find the response using the equation below. Let us recall the types of responses. As we can see, the overdamping and the critical damping responses are similar in that they are not oscillating. They reach the steady state in different times. The overdamping response takes more time. Where the underdamping response is oscillating about the steady state and goes to 0. Forced vibration occurs when the system is subjected to external force. There are 3 types of external forces that can be subjected to the system. We have the external forcing and the base excitation and the rotor excitation. All of them are functions on time. Resonance occurs when the natural frequency of the system equals the natural frequency of the external force. The amplitude of the system is maximized when that happens. There are many examples of resonance. A very common example of vibration resonance is when turning the air conditioning unit on. The compressor force frequency will start at 0 to a specific frequency. until reach a specific frequency, and in between the natural frequency of the system and the force, the frequency will be the same. At this time, resonance will happen, and the AC unit starts to vibrate. Okay. Also, mechanical resonance can produce vibration strong enough to destroy the object in which they occur. For example, soldiers marching over bridges can set up extreme vibrations at bridge natural frequency and shake it apart. For this reason, soldiers break steps to cross a bridge. Another example is Tacoma Bridge in Washington, where the wind caused the bridge to vibrate at its natural frequency, and the bridge collapsed. Base excitations differs than harmonic force excitation in that the excitation is at the base, not the mass, and the excitation is given in terms of displacement, not forces. An example of base excitations are buildings subjected to earthquakes, also packages during transportations, and the design of accelerometers. The displacement transmissibility, or the displacement ratio, is the ratio between the output displacement and the input displacement. It can be obtained by the following equation using the zeta damping ratio and the frequency ratio. Before the frequency ratio of the square root of 2, we need to lower the displacement ratio by increasing the damping ratio zeta, and we can do that by changing the masses or the damping coefficient of the system. After the the frequency ratio of the square root of 2, the displacement ratio will always be less than 1. Force transmissibility is the ratio between the force transmitted to the base and the equivalent spring coefficient multiplied by the displacement of the base. It can be obtained by the following equation. Force transmissibility depends on the damping ratio, and also depends on the frequency ratio. As we can see the chart, at frequency ratio of the square root of 2, the force transmitted to the base is always doubled.
Assalamu alaikum. My name is Muhammad Khudari, and I will continue with you in the presentation. I'm going to talk about the type of forcing, which my teammate Ahmed has explained that we have 3 types of forcing. We have external forcing, which is basically a force applied on the mass, this value over here, and we have base excitation, which we have motion in the base with a value, and finally we have the rotor excitation, which is also called rotating imbalance. We can see you have another mass connected to the main mass that have its own motion. All of this type of forcing have its own particles interest, and we're going to discuss each one of them. Any type of response have divided into 2: steady state and transient. As you can see here in this plot, that this system starts with a transient and is not steady until it finally reach the steady state. And that's what we're going to focus on in our talk, the steady state. First, we're going to talk about the external forcing. As we can see in the system over here, this system gives us this equation of motion. And this is the solution for the steady state of the equation of motion. We can see that the amplitude x equal f dot over m omega n square, and this value over here. This value over here, we can call it magnification factor, and it's also equal x over x dot and equal k x over f dot. If we plot the magnification factor with the frequency ratio, we can see that they all start at 1 magnification factor, and here we have a little amplification and low frequency ratio. But at 1 frequency ratio, we can see that we have large amplification. And this value, which in here we have something called resonance, and it get lower with the if we increase the damping ratio. Basically, our design going to be under the value of 1 of the magnification factor. So we have no amplification and we have high frequency ratio. And if we plot the phase angle with the frequency ratio, we can get the phase angle by using this formula over here. We can see that at 1 frequency ratio and pi over 2 phase angle, all the damping ratios are the same. But if we take 0.1 damping ratio, for example, you can see how it rapidly increased from 0 until it reached pi. While if we take 5 damping ratio, we can see how it increased in the beginning, and after that, after it reached pi over 2, it gets stabilized. This is the second type. It's called basic excitation. For this particular system here, we got the equation of motion. Then we solve for the solution. We have the base A equal the amplitude ui square root k square plus c omega square, and from this we got the amplitude value is equal A over square root of k2 plus c omega square, and we got the angle too. Then we solve for the mass, the steady state solution for the mass, which is equal x the amplitude sine omega t minus alpha minus the phase angle, and from there we got the value of the amplitude and the angle. And if we divide it x over y, we'll get something called displacement transferability. It's equal to this value here. But this value, this formula is not dimensionless. So by using these relations here, we can convert it into dimensionless form, which is basically contains zeta and omegas. Then we plot the displacement transformability with the frequency ratio. As we can see at square root of 2, we can divide into two regions: the amplification region and the isolation region. In the amplification region, if we increase the damping ratio, we can see that the displacement or amplification is decreased, while the exact opposite happened in the isolation region. Second, we have the force transmitted to mass, which is basically the magnitude of transmitted force to the base excitation, and it's equal to m omega square x, where the ft over the ky equal to this formula here. And if we plot the ft of the ky, the base motion, with the frequency ratio, we can see the same thing, that at the square root of 2, all the damping ratios are the same. But in here, the damping ratio increase the excitation. Finally, we have the motion relative to base, which is the difference between x and y, and we call it z. And when we get the steady state solution for the z, will equal the z, the amplitude, sine omega t minus the angle, while z, the amplitude, will equal to this value, this form here. So if we define z over y, we're gonna this form here, then we're gonna transfer it to dimensionless form. And if we plot it with the frequency ratio, you can see that adds 1 frequency ratio, we have resonance, and it's decreased with the increase of the damping ratio, and it's almost all the same in the end, which is this gonna be our design region. Now we're going to talk about the last type of forcing, which is rotor excitation, also called rotating imbalance. If you can see here in the free body diagram, we have the total mass of the system, and this is the unbalanced mass. And the E here is actually the eccentricity. And if we get the equation of motion for this particular system, and we solved it, finally we're gonna get this form here, mx over me. So if you want to get the force on to the mass, so the same thing in the basic excitation, we have first to get this ratio here, which is ft over me omega n square equal to this form. Then we plot it with the frequency ratio. It is the same plot we used in the basic excitation at the square root of 2. All the damping ratios are the same, and the increase the damping ratio actually increase the excitation. And the motion related to the base, we get this ratio here, the mx over the me equal to this form. We use the same laws we used in the basic citation. And which one give us the resonance and the increase of the damping ratio, decrease the amplification. For more details, please visit Dr. Saeed Asiri website. Thank you.